The morning of April 19th, 1944. Henderson Field, Guadalcanal. First Lieutenant James H. Sweat stood beside his F4U Corsair, watching a mechanic named Technical Sergeant Raymond Tex Holloway make an adjustment that would change everything pilots thought they knew about their aircraft's capabilities. Holloway wasn't working on the fuel tank. He was working on something far more dangerous, far more ingenious. He was preparing to inject a volatile mixture of water and methanol directly into the cylinders of the most powerful piston engine ever mounted on a carrier fighter. What happened next would redefine the boundaries of what was possible in the Pacific theater, where distance wasn't measured in miles, but in the difference between returning home and ditching in an ocean that stretched endlessly in every direction. This is the story of how mechanics and engineers transformed the Corsair from an already formidable fighter into something the Japanese came to call whistling death, and how the quest to fly further, fight longer, and survive another day drove American ingenuity to its absolute limits. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The F4U Corsair was born from desperation disguised as ambition. In 1938, the United States Navy issued a specification that seemed almost impossible. They wanted a carrier-based fighter capable of over 400 miles per hour, armed heavily enough to destroy enemy bombers, yet capable of landing on a pitching deck in the middle of the Pacific Ocean. The specification arrived at a moment when war clouds were gathering over Europe and Asia, when American military planners understood with crystalline clarity that the next war would be won or lost by whoever controlled the skies over vast stretches of ocean. Chance Vaught's answer was audacious. Chief Engineer Rex Beisel and his team, which included the legendary Igor Sikorsky, decided to build the smallest possible airframe around the largest, most powerful engine available. The Pratt Whitney R-2800 double-wasp radial engine produced 2,000 horsepower, an extraordinary figure for 1938, but mounting such a massive engine created an immediate problem. The propeller required to handle that power would be over 13 feet in diameter. Make the landing gear tall enough to provide propeller clearance, and the aircraft becomes unstable on carrier decks. Make it too short, and the propeller strikes the deck. Beisel's solution became the Corsair's most distinctive feature, the inverted gull wing. By angling the wing downward at its root where it met the fuselage, then back upward toward the tips, the designers could use relatively short, sturdy landing gear while still providing adequate propeller clearance. The solution was elegant in its geometry, but it created new challenges in fuel storage, structural integrity, and pilot visibility. Every design decision in aircraft engineering is a compromise between competing necessities, and the Corsair embodied this truth in its very bones. On May 29, 1940, test pilot Lyman A. Bullard Jr. lifted the XF4U-1 prototype off the runway at Stratford, Connecticut. The flight revealed both the aircraft's extraordinary potential and its considerable problems. The Corsair was fast, climbing to altitude with startling rapidity and reaching speeds that made it one of the swiftest aircraft in the world. But it was also difficult to control, particularly during landing. The long nose blocked forward visibility. The aircraft had a tendency to stall without warning. And most troublingly for a carrier-based fighter, it bounced when hitting the deck, a characteristic that could send an aircraft careening into other planes or over the side of a carrier. The Navy's response was measured, but firm. They ordered the Corsair into production, but not for carrier service. Instead, the first operational F4U squadrons went to the Marine Corps, which would fly them from land bases, where the difficult landing characteristics mattered less. This decision, made in early 1943, inadvertently gave the Corsair to pilots who would push it harder, fly it longer, and demand more from it than anyone had imagined possible. By the time Lieutenant Sweat and Sergeant Holloway stood on that runway in Guadalcanal in April 1944, the Corsair had been in combat for over a year. Marine pilots flying from primitive island airstrips had learned the aircraft's capabilities and limitations through the harsh teacher of combat experience. They learned that the Corsair could outrun any Japanese fighter, that it could outdive anything in the sky, that its 650 caliber machine guns could saw an enemy aircraft in half. But they also learned something that haunted every mission, every patrol, every combat sortie in the vastness of the Pacific. Range. The original F4U-1 carried 237 gallons of fuel in a self-sealing tank located in the fuselage, directly ahead of the cockpit. Additional 62-gallon auxiliary tanks were installed in each wing's leading edge, just outboard of the guns. In theory, this gave the Corsair a total internal fuel capacity of 361 gallons. But those wing tanks were not self-sealing. A single bullet strike could turn them into flaming death traps. Pilots in combat zones often flew with the wing tanks empty or drained, relying solely on the 237-gallon main tank. The mathematics of this limitation were brutal. The R-2800 engine consumed fuel at varying rates depending on power settings, altitude, and the mixture controls. At economical cruise settings around 5,000 feet, the engine burned approximately 42 gallons per hour. At maximum continuous cruise at 10,000 feet, consumption jumped to 83 gallons per hour. At combat power, the engine devoured fuel at staggering rates, 240 gallons per hour at full military power at 19,000 feet. Calculate the margins, and the reality becomes stark. With 237 gallons of usable fuel and maintaining economical cruise, a Corsair had roughly 5.5 hours of endurance. That translated to approximately 1,000 miles of total range. But this was theoretical range, the distance achievable in perfect conditions with no combat, no evasive maneuvering, no time spent at high power settings climbing to intercept altitude or engaging enemy aircraft. In practical terms, pilots counted on roughly 400 miles of combat radius. Fly out 200 miles, engage the enemy, and fly back with minimal fuel reserve. Push beyond that envelope, and you were gambling with mathematics that never forgave optimism. The Pacific Ocean is the largest body of water on Earth, covering more than 60 million square miles. Japanese-held islands were scattered across thousands of miles of that emptiness. Air bases were separated by distances that made every mission a calculated risk, every patrol an exercise in fuel management. Pilots developed rituals around fuel consumption. They memorized their engine's fuel flow characteristics at different power settings and altitudes. They calculated and recalculated range, factoring in headwinds, the weight of external stores, the fuel burned during combat. They learned to lean their mixture controls precisely, walking the fine line between engine efficiency and catastrophic failure from running too lean. And still, the ocean claimed aircraft not through enemy action but through simple arithmetic, fuel exhaustion. This was the operational reality when Sergeant Holloway began working on the water-methanol injection system. The technology wasn't new. German engineers had pioneered the use of water injection to boost engine power during the 1930s. The principle was elegantly simple. Inject a mixture of water and methanol, usually in a 50-50 ratio, into the engine's supercharger or directly into the cylinders. The water portion would evaporate, cooling the intake charge and allowing higher manifold pressures without detonation. The methanol, being alcohol, would combust, contributing additional power. Together, these effects could boost an engine's output by 10 to 25% for short periods. But here was the paradox, the detail that makes the title's promise both true and misleading in equal measure. Water-methanol injection didn't extend range. It reduced it. The system allowed pilots to extract more power from their engines for brief periods, 5 minutes of war, emergency power, that could mean the difference between catching an enemy aircraft or losing it, between climbing above an attack or being caught flat-footed. But operating at these higher power settings consumed fuel faster. Much faster. The injection system itself carried approximately 20 to 30 gallons of water-methanol mixture stored in a tank just forward of the pilot. This added weight without adding range. So how, then, did this modification allow Corsairs to fly 400 miles further on the same tank? The answer lies not in what the system did, but in what it allowed pilots to do differently. And the real story, the story that matters, isn't about a single mechanic's innovation, but about a systematic transformation in how the Navy and Marines approached the fundamental problem of operating fighter aircraft across oceanic distances. The water-methanol injection was one piece of a larger puzzle, and understanding that puzzle requires following the thread through the dirty, diesel-stained workshops of Pacific Island airfields, where men like Sergeant Holloway performed modifications that the Bureau of Aeronautics in Washington would never officially sanction, but couldn't afford to prohibit. The R-2800-8W engine, the W indicating the water injection capability, began appearing in late-model F4U Corsairs in mid-1943, but these were factory installations, carefully engineered and tested. What Holloway and mechanics like him across the Pacific were doing was different. They were adapting, improvising, finding ways to make the system work in conditions that would horrify engineers accustomed to clean test facilities and controlled variables. Henderson Field in April 1944 was not a pristine environment. The airstrip was carved from jungle, surrounded by coconut palms and ankle-deep mud. Humidity approached 100%. Salt air corroded metal faster than mechanics could apply protective coatings. Fuel arrived in drums that had been baking in the tropical sun. Its octane rating degraded, its consistency contaminated with moisture and sediment. Under these conditions, the water-methanol injection system, which required precise mixtures and clean lines, should have been a maintenance nightmare. Often it was. Holloway's innovation wasn't creating the system, it was making it reliable under impossible conditions. He discovered that by slightly adjusting the injection nozzles and modifying the fuel mixture ratios to account for the degraded fuel quality, he could maintain consistent power output. More importantly, he found ways to plumb additional water-methanol storage into spaces where it shouldn't fit, giving pilots a larger reservoir of emergency power. These modifications spread through the informal network of marine mechanics, shared in the same way submarine crews later shared torpedo modifications. Through word of mouth, sketched diagrams passed between squadrons, and the kind of practical wisdom that exists outside official channels. But the real transformation in Corsair range came from a different source entirely, one that had nothing to do with water injection and everything to do with weight, drag, and the physics of flight. In early 1943, squadrons began experimenting with external fuel tanks, drop tanks. These were auxiliary fuel containers carried under the fuselage or wings that could be jettisoned when empty or when entering combat. The concept was simple. The execution proved maddeningly complex. The Navy had authorized centerline drop tank pylons for the F4U variant introduced in April 1944. The same month, Lieutenant Sweat stood watching Sergeant Holloway work. These pylons could carry a single 150-gallon drop tank under the fuselage, or later, twin-rack plumbing allowed for an additional belly drop tank, 150 gallons. At economical cruise, that represented nearly 4 additional hours of flight time, approximately 600 additional miles of range. Here was the magic, if you wanted to call it that. A Corsair carrying 150 additional gallons in a drop tank, flying at optimized cruise settings with the water-methanol system available for emergency power when needed, could extend its effective range from roughly 1,000 miles to nearly 1,400 miles. The operational combat radius jumped from 400 miles to potentially 600 miles or more, depending on mission profile and fuel management. But this wasn't a simple matter of bolting on a tank and flying further. The drop tanks created drag, approximately 10 to 15 miles per hour reduction in maximum speed. They were unaerodynamic, hanging beneath the fuselage like pregnant bellies. Worse, they were vulnerable. A single bullet strike could ignite the fuel, turning the drop tank into a bomb strapped to your aircraft. Pilots had to know when to drop them, when carrying the extra weight and drag was worth the fuel, and when jettisoning them meant the difference between being caught slow and low or having the speed to fight. The doctrine emerged from necessity rather than planning. Marine squadrons discovered through trial and error that the optimal approach was to climb to altitude on internal fuel, switch to the drop tank for cruise, then either drop it before entering combat or, if fuel state allowed, continue drawing from it until nearly empty. This required constant attention to fuel management, switching between tanks at precise moments, monitoring fuel pressure and engine performance for any sign of contamination or feed problems. And here was where Holloway's modifications to the water-methanol system became crucial. Not for extending range, but for providing insurance. A pilot who had burned through his drop tank and most of his internal fuel, flying the razor's edge between making it home and ditching in the ocean, could use those 5 minutes of war emergency power to climb above weather, to sprint the final miles to base, or to gain altitude for a dead-stick glide if the engine quit. The water-methanol injection didn't make the fuel last longer. It made the fuel that remained more effective at critical moments. Technical Sergeant Holloway understood this distinction in a way that separated competent mechanics from truly exceptional ones. He wasn't trying to rewrite physics. He was trying to give pilots options when they had none. His modifications to the injection system focused on reliability, ensuring that when a pilot pushed the throttle forward and engaged war emergency power, the system would deliver. Every time. Without hesitation, because in combat, hesitation measured in seconds could mean the difference between life and death. By summer of 1944, the Corsair had evolved into the F4U 1D variant that incorporated many of these lessons. The factory installation included the R2800-8W engine with water injection as standard equipment. The wing-mounted fuel tanks, which had proven too vulnerable, were removed in favor of increased external stores capability. The aircraft could now carry not just a centerline drop tank, but also 8 5-inch rockets or 2,000-pound bombs. This transformation from pure fighter to fighter bomber required accepting certain compromises. The external stores created drag. The bomb pylons and rocket rails, even when empty, reduced speed by several miles per hour. But the tactical flexibility proved worth the cost. A Corsair could fly escort with drop tanks, engage enemy fighters, jettison the tanks, and still have enough fuel to strafe ground targets before returning to base. Or it could carry bombs to a distant target, deliver them with devastating accuracy, and retain enough fuel to patrol the area before heading home. This kind of operational flexibility was impossible with the earlier F4U1 model, limited to internal fuel and no provision for external stores. The Japanese noticed. By mid-1944, intelligence reports reaching Tokyo painted an increasingly desperate picture. American fighters were ranging further from their bases. They were appearing over targets that should have been beyond their reach. Japanese commanders, accustomed to calculating safe distances based on known enemy fighter ranges, found their calculations no longer valid. The whistling death could be anywhere. Lieutenant Sweat's mission on April 19, 1944, exemplified this new reality. His target lay 450 miles from Henderson Field, a distance that would have been impossible for early-model Corsairs operating on internal fuel alone. But Sweat's F4U-1D carried a 150-gallon centerline drop tank. The mission profile was straightforward in theory, complex in execution. Climb to 15,000 feet on internal fuel. Switch to drop tank for the transit to target area. Drop the tank before engaging enemy aircraft. Fight on. Internal fuel. Return home praying that fuel calculations were accurate. Sergeant Holloway's final check of the water-methanol system took less than 5 minutes. He verified the tank level, 28 gallons of the mixture, checked the injection nozzles for contamination, tested the activation switch in the cockpit, verified that the system armed properly at high power settings. Then he stepped back and offered the ritual comment that mechanics gave to pilots they respected. "She'll get you there and back, sir. Just don't get crazy with that injection unless you absolutely need it." Sweat nodded. He understood the subtext. The water-methanol injection was emergency power. 5 minutes maximum before risking engine damage from excessive cylinder head temperatures. Use it to escape danger. Use it to catch an enemy aircraft. Use it to climb above weather. But don't use it casually, because every minute at war, emergency power consumed fuel at rates that made mockery of careful flight. Planning. The mission proceeded according to plan until it didn't. Plans in combat rarely survive contact with reality. Sweat's flight reached the target area to find not the expected Japanese bomber formation, but a swarm of Zero fighters escorting a convoy. The tactical situation demanded immediate decisions: engage and risk running low on fuel, or abort and return without engaging. Sweat chose to engage. The Corsairs' advantages over the Zero were well understood by 1944. Superior speed, superior dive performance, heavier armament, better armor protection. The Corsair could not outturn a Zero, but it didn't need to. American fighter doctrine emphasized boom and zoom tactics. Dive from altitude, make a single firing pass, extend away using superior speed, climb back to altitude, repeat. Never turn with the Zero. Never try to fight its fight. But doctrine assumed adequate fuel. Sweat's fuel state was marginal. The drop tank was already gone, jettisoned as he dove into the engagement. His main tank showed approximately 120 gallons remaining. At combat power, that represented perhaps 30 minutes of flight time, less if he needed full military power for extended periods. The distance back to Henderson Field required at least 90 minutes at economical cruise. The mathematics didn't work. This was the moment Holloway's modifications mattered, not for extending range, but for compressing time. Sweat needed to disengage quickly, climb to optimal cruise altitude, and begin the long flight home before his fuel situation became critical. The water-methanol injection gave him the power to execute a vertical climbing reversal that broke contact with pursuing Zeros. 5 minutes of war emergency power, the engine thundering at manifold pressures that would have destroyed it without the cooling effect of water injection. The Corsair clawed skyward, reaching 18,000 feet before Sweat throttled back and switched off the injection. Now came the delicate part: fuel management for survival. Sweat leaned his mixture to the edge of roughness, adjusted his propeller pitch for maximum efficiency, calculated and recalculated his fuel consumption against distance remaining. Every pilot in the Pacific knew these calculations by heart: fuel flow in gallons per hour, speed in miles per hour, distance remaining in nautical miles. Convert everything to a common unit and solve for time. Then solve for fuel required. Then compare fuel required to fuel available and pray the answer was positive. 90 minutes later, with the fuel gauge showing less than 20 gallons, Henderson Field appeared as a thin line carved from jungle. Sweat's landing was routine, perfect even, but his hands were shaking as he shut down the engine. Holloway was waiting by the revetment. The conversation was brief. Sweat reported the mission. Holloway asked about the injection system. It had performed flawlessly. They shook hands. Nothing else needed, saying. This scene, or variations of it, repeated thousands of times across the Pacific theater. During 1944 and 1945, pilots pushed their aircraft to the limits of endurance, relying on modifications and techniques that existed outside official doctrine, but within the practical wisdom of men who understood that survival depended on extracting every possible mile from every gallon of fuel. The water-methanol injection system became part of that wisdom, not as a range extender but as an emergency power reserve that gave pilots options when fuel state was critical. The F4U variant, which began reaching squadrons in late 1944, represented the culmination of these lessons. The more powerful R2800-18W engine produced 2100 horsepower standard, jumping to 2450 horsepower with water-methanol injection. The aircraft was faster, climbing better, and more capable than any previous Corsair variant, but it also consumed fuel faster. The wing tanks were gone permanently, removed for better maneuverability. Range depended entirely on drop tanks and careful fuel management. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Marine squadrons refined their techniques continuously. They discovered that by carefully managing climb profiles, they could reach cruise altitude while consuming minimal fuel. That cruising at specific speeds, usually around 180 to 200 miles per hour, maximized range while maintaining enough speed for combat maneuverability. That drop tanks, while ungainly, were the single most important range-extending modification available. but they also discovered limitations that no amount of innovation could overcome. The Corsair, for all its capabilities, remained fundamentally an aircraft designed for carrier operations in the relatively confined spaces of the Pacific's island chains. It was not a long-range escort fighter in the mold of the P-51 Mustang, which could fly to Berlin and back carrying even more fuel and operating at higher altitudes where thinner air meant lower fuel consumption. The comparison is instructive. A P-51D Mustang with internal fuel and drop tanks could achieve ranges exceeding 1,500 miles with combat reserves. The Corsair with drop tanks managed perhaps 1,200 to 1,400 miles, and that was pushing fuel management to its limits. The difference lay in fundamental design philosophy. The Mustang was optimized for high-altitude operations, where turbocharging provided efficient power and thin air reduced drag. The Corsair was optimized for medium and low-altitude operations, where its mechanical supercharger worked well but consumed power and fuel. Neither aircraft was superior in absolute terms. They were optimized for different missions, different theaters, different operational requirements. The Mustang excelled at high-altitude bomber escort over Europe. The Corsair excelled at medium-altitude fighter sweeps and ground attack in the Pacific. Trying to make a Corsair perform Mustang missions or vice versa was an exercise in frustrated expectations. What mechanics like Sergeant Holloway understood was that optimization meant accepting trade-offs. The water-methanol injection traded fuel consumption for power. Drop tanks traded speed and maneuverability for range. Removing wing tanks traded fuel capacity for reduced vulnerability and weight savings. Every modification was a bargain with physics, and physics always extracted payment. The larger story, the story that encompasses Holloway's modifications and thousands of similar innovations across the Pacific, was about an American military culture that empowered people closest to problems to solve those problems. The Bureau of Aeronautics in Washington could design aircraft, factory engineers could optimize production, but mechanics in the field understood operational realities that no amount of theoretical knowledge could replicate. This tension between centralized authority and decentralized innovation defined much of America's success in World War II. Unlike military systems that required strict adherence to doctrine and punished deviation, the American system, at its best, encouraged intelligent adaptation. Mechanics were expected to maintain aircraft according to technical manuals, but they were also expected to solve problems that manuals didn't address. Pilots were expected to follow tactical doctrine, but they were also expected to exercise judgment when doctrine didn't fit reality. Holloway's modifications to the water-methanol injection system fell into this grey area. Nothing he did violated regulations exactly, but nothing he did appeared in official maintenance procedures either. He improvised solutions to problems that the original designers hadn't anticipated because they hadn't operated in the conditions he faced daily. Contaminated fuel, extreme humidity, prolonged storage of chemicals that degraded over time. The injection system as designed worked perfectly in test facilities. Holloway made it work in jungle airstrips. This pattern repeated across every aspect of Pacific air operations. Armorers modified bomb racks to carry loads the original design didn't accommodate. Radio technicians jury-rigged communications equipment to work in conditions that exceeded design specifications. Engine mechanics adjusted timing and mixture settings to compensate for fuel quality that varied wildly from one shipment to the next. The cumulative effect of thousands of small innovations was profound. American aircraft in the Pacific operated with reliability rates that Japanese forces, struggling with supply shortages and limited maintenance infrastructure, couldn't match. A Corsair squadron could launch 20 aircraft on a mission with reasonable confidence that 18 or 19 would return. Not all would return because of enemy action, but most would return because mechanics like Holloway ensured they were mission-ready. Compare this to Japanese squadrons operating from bases like Rabaul in late 1943 and early 1944. Japanese pilots were skilled, their aircraft were capable, but their maintenance infrastructure was collapsing. Parts shortages meant cannibalizing aircraft to keep others flying. Fuel shortages meant mixing low-octane fuel with higher grades, causing engine problems. The mathematics of attrition favored whoever could maintain operational readiness, and America's industrial base plus its culture of practical innovation created insurmountable advantages. The story of the Corsairs' extended range is really a story about systems, not just the fuel system or the engine system, but the entire system of aircraft production, pilot, training, maintenance infrastructure, supply logistics, and tactical doctrine that allowed the aircraft to operate effectively. Water-methanol injection was one component. Drop tanks were another. Fuel management training was a third. Mechanics like Holloway were a fourth. Remove any single component and the system degraded. Optimize all components together, and you achieved capabilities that seemed impossible, examining any single element. By late 1944, Corsairs were regularly flying missions that would have been inconceivable 2 years earlier. Not because the aircraft had fundamentally changed, though improvements certainly helped, but because every aspect of their operation had been refined through hard-won experience. Pilots understood their aircraft's capabilities intimately. Mechanics knew exactly which modifications improved reliability without compromising safety. Supply officers ensured that critical items like water-methanol mixture arrived in quantities sufficient for operational needs. Intelligence officers provided accurate target information that minimized wasted flight time. The result was an operational tempo that Japanese forces couldn't match. American squadrons could fly multiple missions daily, reaching targets across hundreds of miles, maintaining combat air patrols that provided near-continuous coverage, and doing all this while sustaining acceptable loss rates. The Corsair wasn't just a fighter aircraft, it was the centerpiece of an integrated system of air power projection. Lieutenant Sweat's mission in April 1944 was one sortie among thousands, but it illustrates the human dimension of these technical achievements. Every mission was a calculated risk. Every takeoff required faith in the mechanics who maintained your aircraft, faith in the engineers who designed it, and faith in your own skill to manage fuel, ammunition, and tactics in ways that brought you home alive. The water-methanol injection system represented one small margin of safety in a profession where margins were measured in gallons and minutes. The psychological impact of extended range capabilities was perhaps as important as the tactical impact. Japanese commanders had relied on distance as a defensive barrier. Bases located 500 miles from the nearest American airfield had been functionally safe from fighter attack. By 1944, that safety had evaporated. American fighters could appear anywhere, stay longer, fight harder. The psychological effect of this ubiquity cannot be overstated. Japanese pilots knew that every mission might bring them into contact with Corsairs. Japanese ground forces knew that air support could not be guaranteed because American fighters dominated the skies. This dominance had cascading effects throughout the Pacific theater. Japanese resupply convoys had to sail at night and hide during the day. Japanese aircraft had to be dispersed and camouflaged to avoid destruction on the ground. Japanese commanders had to assume American air superiority when planning any operation. The strategic initiative passed to the Americans, not just because they had more aircraft, though they did, but because their aircraft could project power across distances that Japanese forces couldn't effectively counter. The technical story of the Corsairs' range improvements also reveals something profound about engineering trade-offs and the evolution of combat aircraft. When Rex Beisel's team designed the original F4U in 1938 and 39, they optimized for speed, firepower, and carrier compatibility. Range was important but not paramount, because the Navy's operational concept envisioned carrier-based fighters operating within relatively close proximity to their floating bases. The carriers would position themselves within range of targets, launch strikes, and recover aircraft. Long-range independent operations were not the primary mission profile. The reality of Pacific warfare shattered these assumptions. Carriers were valuable targets that couldn't be risked unnecessarily. Land-based operations from island airfields became crucial. The distances involved exceeded anything anticipated during the design phase. The aircraft designed for one mission profile had to adapt to another, fundamentally different mission profile. That it succeeded is testament to both the underlying design's excellence and the adaptability of the people who operated it. Consider what modifications couldn't easily be made. The Corsairs' fuel capacity was limited by available space in the fuselage. The inverted gull wing design, while elegant, meant that wing fuel tanks had to be located in vulnerable positions. The aircraft's center of gravity restrictions limited how much weight could be added and where. The R-2800 engine's fuel consumption was a function of its power output and design. You couldn't fundamentally change these characteristics without redesigning the entire aircraft. What you could change were the peripheral elements. Add external fuel tanks. Optimize fuel management procedures. Provide emergency power systems that gave pilots options in critical situations. Improve maintenance reliability so that more aircraft were mission-ready. Train pilots in fuel conservation techniques. These changes, accumulated and integrated, transformed operational capabilities without changing the fundamental aircraft. This approach, incremental improvement rather than revolutionary redesign, characterized American aircraft development throughout World War II. The B-17 bomber evolved through multiple versions, each incorporating lessons from combat experience. The P-51 Mustang went from mediocre performer to war-winning escort fighter by changing engines and refining details. The F-6F Hellcat, the Corsairs' contemporary and competitor, achieved remarkable success through straightforward design, executed well rather than cutting-edge innovation. The water-methanol injection system fits this pattern. The technology existed before the war. German engines used it extensively, but American implementation focused on reliability and ease of maintenance rather than maximum performance. The system added approximately 250 horsepower to the R-2800-8W engine for 5-minute intervals. This wasn't enormous in percentage terms, roughly 12% power increase, but it came at moments when that extra power could save a pilot's life. Sergeant Holloway's understanding of the system went beyond its technical specifications. He understood its operational context. When a pilot engaged water-methanol injection, it meant something had gone wrong, or was about to go very wrong. It meant enemy aircraft closing faster than expected. It meant weather requiring a climb above safe altitudes. It meant fuel state critical and needing every possible advantage to reach home. The injection system was not a routine tool. It was emergency equipment, and emergency equipment had to work flawlessly when called upon because there were no second chances. This reliability focus drove Holloway's modifications. He didn't try to extract more power or extend the injection time beyond safe limits. He ensured that the system would activate instantly when needed, deliver consistent power throughout its operating envelope, and shut down cleanly without engine damage. These might seem like modest goals, but achieving them under field conditions required deep understanding of both the machinery and the environment in which it operated. The broader lesson extends beyond aviation or even beyond World War II. Complex systems succeed or fail based on the competence and dedication of the people who operate and maintain them. You can design the most advanced technology in the world, but if the mechanics can't keep it running or the operators can't use it effectively, it's worthless. The Corsair succeeded because every link in the chain, from factory workers in Connecticut to mechanics on Pacific Islands to pilots over enemy territory, performed their roles with skill and commitment. By war's end, the F4U Corsair had compiled a record that speaks for itself. Over 12,500 aircraft produced, a kill ratio against Japanese aircraft exceeding 11-1. Service with the Navy, Marines, Royal Navy Fleet Air Arm, and Royal New Zealand Air Force. Combat operations spanning from 1943 through the end of the war and continuing into Korea. The aircraft remained in production until 1952 and in frontline service until the 1960s with some air forces. But statistics, however impressive, don't capture the human experience. They don't capture what it felt like to fly a Corsair on a long-range mission, watching the fuel gauge creep toward empty while the ocean stretched endlessly below. They don't capture the relief of seeing home base appear on the horizon with barely enough fuel to land. They don't capture the relationship between pilot and mechanic, the trust that had to exist because lives depended on it. Lieutenant Sweat survived the war. He would eventually receive the Medal of Honor for actions during a different mission, one where he shot down 7 Japanese aircraft in a single sortie while flying an F-4F Wildcat earlier in the war. But he later said that the mission in April 1944, the one where Sergeant Holloway's modifications to the water-methanol system gave him the power to disengage and begin the long flight home with fuel critically low, that mission stayed with him more than the one that earned him the medal. "You remember the times you almost didn't make it back," Sweat said in an interview decades later. "The times when everything had to work perfectly and did. The times when you knew that if your mechanic had been careless, or if you had been less diligent about fuel management, or if weather had been slightly worse, you wouldn't be here talking about it. Those are the missions that remind you that war isn't about individual heroism. It's about thousands of people doing their jobs correctly so that everyone can come home." Sergeant Holloway never received public recognition for his modifications to the Corsairs' water-methanol injection system. His name doesn't appear in official histories or technical manuals. He was one of thousands of mechanics who made victory possible through unglamorous work in difficult conditions. After the war, he returned to Texas, worked as an automotive mechanic, and rarely spoke about his service. The few times he did, he downplayed his contributions. "I just kept the birds flying," he would say. "That was my job." But his legacy lives in every Corsair that made it home on fumes, every pilot who used that 5 minutes of war emergency power to escape danger, every mission completed successfully, because the aircraft performed exactly as needed when needed. That's the real story of the Corsair's extended range. Not a single brilliant innovation, but 1,000 small improvements made by dedicated people who understood that excellence in details meant the difference between life and death. The titles promise that one mechanic's fuel mix made Corsairs fly 400 miles further contains truth if you understand it correctly. Not that water-methanol injection extended range, because it didn't, but that the culture of innovation and adaptation that Holloway represented, the willingness to modify and improve and optimize within the constraints of physics and engineering, that culture enabled Corsairs to operate far beyond their original design parameters. The 400 miles came from drop tanks, not injection systems. The 400 miles came from better fuel management training. The 400 miles came from pilots who understood their aircraft intimately and flew, to them with precision. The 400 miles came from mechanics who ensured every system worked reliably. The 400 miles came from the entire integrated system of American air power in the Pacific. But Holloway's modifications mattered because they were part of that system. The water-methanol injection gave pilots emergency power when they needed it most. That emergency power sometimes meant the difference between making it home or not, and making it home meant flying another mission, contributing to the cumulative attrition that eventually overwhelmed Japanese air power. The Japanese understood what was happening. Intelligence reports from late 1944 describe American fighters with inexplicable range, operating far from known bases. Japanese pilots reported encounters with Corsairs at locations that should have been beyond their reach. Japanese commanders struggled to explain how American aircraft could maintain such operational tempo across such vast distances. They attributed it to superior logistics, which was true. They attributed it to more aircraft, which was also true. But they missed the deeper reality. American success came from a military culture that empowered innovation at every level, that valued results over rigid adherence to procedure, that trusted mechanics and pilots to solve problems in ways that headquarters couldn't anticipate. This culture created advantages that went far beyond simple numerical superiority. The Corsairs' story is ultimately about people making the most of the tools they had. The aircraft itself was excellent, but excellence alone doesn't win wars. Wars are won by logistics, by maintenance, by training, by the unglamorous work that keeps aircraft flying and pilots effective. Sergeant Holloway represented this truth. His modifications to the water-methanol injection system were technically modest, but operationally crucial. They exemplified the kind of practical wisdom that exists outside official channels, but inside the knowledge of people who actually do the work. When we tell stories of World War II aviation, we often focus on dramatic combat, on aces and dogfights and bombing runs. These stories matter because they represent human courage and sacrifice. But alongside them should be stories of mechanics working in tropical heat to keep engines running, of pilots carefully managing fuel on long overwater flights, of engineers solving problems that emerged only in combat conditions. These stories reveal a different kind of heroism, the heroism of competence and dedication and professional excellence. The Corsair flew 400 miles further, not because of magic, but because of mathematics, engineering, and human skill applied with precision and purpose. Water-methanol injection was one variable in a complex equation. Drop tanks were another. Fuel management was a third. Maintenance reliability was a fourth. Tactical doctrine was a fifth. Integrate all variables correctly, and the aircraft's capabilities expanded dramatically. This is the lesson that transcends aviation and World War II. Complex systems achieve extraordinary results when every component is optimized and every person understands their role within the larger system. The Corsair's extended range emerged from systematic excellence across the entire chain of aircraft operation. Remove any link, and the system degraded. Strengthen every link, and capabilities that seemed impossible became routine. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. Sergeant Raymond Holloway and Lieutenant James Sweat never met again after the war. Holloway didn't attend squadron reunions, preferring to let his wartime service remain quietly in the past. Sweat went on to a distinguished career, speaking occasionally about his experiences. But both men, in their different ways, represented the truth at the heart of this story. Victory in war comes not from individual genius, but from collective competence, not from dramatic innovations, but from 10,000 small improvements, not from heroes who stand alone, but from ordinary people doing extraordinary work in difficult circumstances. The Corsair flew further because people like Holloway and Sweat, mechanics and pilots, made it fly further through skill, knowledge, and unwavering commitment to their mission. That's the real story of the fuel mix that changed Pacific air warfare. Not a single modification by one mechanic, but a culture of innovation that empowered everyone to contribute to success. The Corsair became whistling death, not because it was invincible, but because the people who flew it and maintained it were professionals who extracted every possible advantage from the tools they had. In the final accounting, this matters more than kill ratios or production numbers. It matters because it reveals how excellence is actually achieved through patience, dedication, attention to detail, and the quiet heroism of doing your job correctly when lives depend on it. Sergeant Holloway understood this, Lieutenant Sweat understood this, and in the end, this understanding made all the difference. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.